Okay, thank you very much, Professor Ayman Badawi. So if we don't have more questions, Mr. Muhammad Mahmoud Shamsuddin, I think we can go to the other talk.
Thank you very much. Thank you very much. So if there is no question,
yes.
Let's wait a few seconds until Professor Antonella Perucca join us.
She's with us. She's with us. She is with us.
Hello, everyone.
Hello.
Hello. She is with us. So the next talk will be presented by Professor Antonella Perucca. I don't know if I spelled the word correctly. Yes?
Yeah, perfect.
Yeah. From University of Luxembourg, from Luxembourg. It's about Artin's primitive root conjecture and related problems. So welcome, Professor Antonella. Go ahead. You have 30 minutes.
Okay. Yeah, so I try to share my screen in case Muhammad has my slides, in case something bad happens, but let me try to. Okay, so, okay. You should now see my screen, so I just need to enter full screen, I suppose. Can you still hear me?
Yes.
Okay, so now you should see my slides. You should hear me. So yes. I think we are good to go, right?
Yes. Yeah, go ahead.
Okay. Yeah. So thank you very much. So thank you very much for the invitation. I like very much to give online talks. It's very convenient to be at home and be able to meet people, give talks. Yes. So today I will speak about Artin type problems. So problems related to Artin's conjecture on primitive roots. And I've worked on this subject, say, starting last year with Olli Gerviniemi from the University of Turku and Pietros Goba from the University of Luxembourg. So just, so they are not here, but just that, so that you know them. So Olli is a PhD student of Kaisa Matomaki. So she's a very strong analytic number theorist, and Olli as well. But he's leaving mathematics by free choice very soon. And Pietros Goba, who has been a PhD student of mine. And we have worked a lot on Kummer theory, which is related to Artin's conjecture. And yeah, so last year we just evolved into more direction of Artin's conjecture. So Artin's conjecture. So Artin's conjecture on primitive roots. I would like first to remind you what a primitive root is. So in this talk, I decided to keep things very simple. So I just work over the rational numbers, and in particular, just with integers, just to give you a glimpse about this conjecture. And you can imagine that it's done also not only for the rational numbers, but for number fields and for other kind of fields. But let's keep it simple. Let's take integers and reduce the integer modulo primes. So P is a prime number, and you have the reduction map that you know from the bachelor. And if you reduce an integer A modulo P, where P doesn't divide A, then the class A modulo P is non-zero. So it lies in the group Z over PZ star, so without the zero, which is a group for the multiplication. And for the multiplication, it is a cyclic group of order P minus 1. And we say that A is a primitive root modulo P if whenever the A modulo P generates the whole group. So this is the cyclic group. So saying that it generates means precisely that the order is P minus 1, or equivalently, that if you take the subgroup generated by this element, it is everything, it is the whole group. So the index of the subgroup is 1. So from this slide, I would like you to retake that Artin's conjecture, it's about primitive roots. So we want our reduction modulo P to generate the whole group, but in fact, it is about the index, because asking A modulo P to be a primitive root, it's precisely asking A modulo P, so the subgroup generated by A modulo P, to have index 1. Okay, so in the next slides, when I speak about Artin's conjecture, I will speak about having index 1. That's what we want. And if you're not familiar with the index, when there is something that you should know, it's very basic, but it's about what happens to the index if you take the power of the element. So suppose that you are in this group Z modulo PZ star, and you have a generator. So generator G modulo P that has index 1. Now, if you take a power of it, well, maybe it's not a generator anymore. So what happens is that if you raise it to a power M, which is co-prime to P minus 1, so co-prime to the order of the group, then you still have a generator, nothing happens for the index. But if you raise it to some power which divides the order of the group, say you take the power D, where D divides P minus 1, then the index becomes D. Okay, so so this is a basic remark of group theory, but for us it will be important, because if you take start from an integer A, say not 0, not plus minus 1, say a reasonable integer A, and we reduce it modulo P that doesn't divide A. So this is our setting. What happens if A is a Dth power, okay? So with D dividing P minus 1. Well, if A is a power, then A modulo P is a power. And because D divides P minus 1, being a Dth power means that D divides the index. So what I'm saying is that if you take a reduction such that D divides P minus 1, if A is a Dth power, there is no chance that A is a primitive root, because the index cannot be 1, will be divisible by D. So in particular, this would be important for the conjecture, if D equals 2, so if A is a square, then A modulo P is a square, and we conclude that the index is even when 2 divides P minus 1. But in fact, 2 divides P minus 1 for every odd prime. So we come to the remark that if A is a square, there is no chance that we will find that it will be a primitive root for P larger than 2. So in fact, the formulation of Artin's conjecture excludes squares, so squares are bad. And the reason is precisely the following. 2 divides P minus 1 for all primes except P equals to 2. And the index of A modulo P will be even for all odd primes, which implies in particular that A modulo P will not be a primitive root for odd primes. And here comes the conjecture. So A, an integer, not 0 and not plus minus 1. So not 0 is pretty clear from the statement. Plus minus 1, it's, well, these are the roots of unity in Z. But so in any case, we take a reasonable integer A, and we suppose that it's not a square because of the obstruction I just explained you. So if A is not a square, then everything is good. You can find many primes such that A is a primitive root modulo P. So you can find infinitely many primes, but even better, you can find a positive density of primes. So the density is a concept of analytic number theory. It's defined with a limit. Basically, you're counting primes. But if you have not seen about density for this talk, you can replace density with proportion. So the theorem says that there is a positive proportion of the primes such that A is a primitive root. So you can imagine, for example, for 50% of the primes, A is the primitive root, or for 10% of the primes, A is the primitive root. So you get a positive proportion of primes such that A is a primitive root. Now, which proportion? So which density? So there is a nice expression for this density. So I like this very much. It's an infinite sum over mu of n. So mu of n is the Möbius function. It is 0 if n is not square free. So n is a positive integer. If n is not square free, for example, 12, mu of 12 is 0. But if n is square free, for example, 6, then mu of n is the parity of the number of prime divisors. So if you have a prime, you have an odd number of prime divisors, so you have -1. If you have the product of 2 primes, +1, product of 3 primes, +1. So alternatively, plus or -1 according to the number of prime divisors. But so in any case, for this formula, you could imagine that here in the numerator, you have plus or -1. So it's just a sign. So you make an alternate sum, where alternate depends on the Möbius function, of the inverse of some degrees. So the degrees of some number fields, so namely if you take n as parameter, you have to consider the degree of the number field, which is obtained starting from Q by adjoining the nth roots of unity, so the nth cyclotomic field, and the nth roots of your element. So this is what I call cyclotomic Kummer extension, because you have a cyclotomic extension, and over it you have the Kummer extension because you take the roots of your element. And this I studied very much in the past. So for many years, I've worked on Kummer theory and I studied these degrees. Okay, so in any case, you have this expression, but say in many cases, these expressions is easy. So in many cases, this expression is an infinite product over the primes of 1 minus 1 divided by L times L minus 1. So which looks clearly easier than this expression concerning number fields. And this product, it's called Artin's constant. And the density, well, in many cases, the density will be precisely Artin's constant, but in general, it will be a rational multiple of Artin's constant. For example, 3/2 of Artin's constant. So what I told you in this slide is a simplification of the Artin's conjecture on primitive roots, because the theorem is not only about the density, it's the asymptotic as well. But so in any case, this conjecture is open in the sense that it was been proven by Hooley in 1967, so 40 years after it has been announced. But it has been proven only conditionally under the generalized Riemann hypothesis. So if you truly believe in GRH, then it has been proven. But if you still have doubts over GRH, you might still hope that one day an unconditional proof will be found. And the reason why GRH is needed for the proof is that the GRH allows you a very strong effective version of Chebotarev density theorem. And this is why you need it. So basically, what you need is a strong enough version of Chebotarev density theorem, so a very good error term. And this very good error term, it's only known under GRH. So this is just about a bit of the story. Let me explain the density a bit more. Okay, so above the same expression as before about the plus minus sign and these degrees of number fields. So how do we come to that density? So we come to that density because we want the index of the reduction of A to be 1, but saying that the index is a positive integer. So saying that it is 1 precisely means that there is no prime divisor. So instead of saying the index is 1, we could say no prime L divides the index. And this allows you to work prime by prime. And in fact, what is not difficult to prove is that the property of L not dividing the index of A modulo P corresponds precisely to the fact that the prime number L, sorry, here's a typo, does not split completely in this number field. So if you want, L divides the index if and only if L splits completely, and L does not divide the index if and only if L does not split completely in this number field. This number field is a cyclotomic Kummer extension as above, just with the parameter L. And if you know Chebotarev density theorem, there is a proportion of primes that split completely in this field, which is the inverse of the degree of the number field. So this is why we get here the inverse of the degrees, that's Chebotarev. Now, what is the problem with Chebotarev? So the problem with Chebotarev is that we have to do infinitely many, to apply Chebotarev density theorem infinitely many times because we have infinitely many L. So in some sense, to get to this density, we need to apply Chebotarev density theorem infinitely many times, which makes sense if we have this strong version of Chebotarev density theorem with good error term, which we have under the generalized Riemann hypothesis. But so in any case, if we are able to apply Chebotarev infinitely many times without having a too large error term, the density here, so we get precisely this expression by the inclusion-exclusion principle. Because we have infinitely many conditions, we want 2 does not split completely in the field related to 2. 3 does not split completely in the field related to 3, and so on. So we have infinitely many conditions, but so when we look at the proportion of primes that we have to exclude, we have to do a inclusion-exclusion, and that is where the sign comes from. So the sign is precisely the plus or minus that you get from the inclusion-exclusion principle. And okay, and the Artins constant you get, supposing that the field extensions made with L are linearly independent, which is not always the case. But yeah, if they are, you get precisely this formula, which is Artins constant is roughly 37% of the primes are good if you suppose the fields to be linearly independent. But they, in general, they are not. So index map. So what we study with Olli and later with Pietro is the generalization of this question, because we don't only require the index to be 1, we just ask, what is the index? And in fact, we also take several integers and we look at simultaneously the index or the reductions of these numbers. So we study a tuple of indices. So we take our integers a1 to an, we reduce them modulo p, look at their indices, make a tuple out of it, and then we ask, what's this tuple? So clearly, this tuple has some conditions on it if the integers are dependent. For example, they're all the same, you get a constant tuple. So in general, we want to study this tuple. So something which is good, which is happening, is that a tuple either happens only for finitely many primes, or it happens very often with a positive density. And what we find out is that this map is sufficiently regular, so we are able to compute the index with an explicit procedure. So there are some dependencies between these indexes, but in fact, we can get hold of them. And okay, and in fact, if you compose this map, so this map with the L-adic valuation, so you have integers here. If you take the L-adic valuation of these integers, you find tuples which do not depend on L if L is sufficiently large. So in fact, this map looks very mysterious, but it's very regular, and this is what helped us pinning it down. And in fact, there is even something better. If you suppose that your elements are multiplicatively independent, this image is large, you have all multiples of some tuple that you can compute. And in fact, it's very easy to say if a tuple is in the index, because if you start with a generic tuple, then the question, is it in the index? That would be infinitely many questions because you have infinitely many tuples. But in fact, you can replace your tuple by a small tuple because you can take the GCD of the entries with the entries of this fixed tuple. So what this means is that because of the regularity of the problem, computing the image of the index map amounts to finitely many questions. So we just have to check whether which of these finitely many tuples belong to the image. And this is clearly some finite and doable algorithm. And then, let me come to some examples, if you want. So now let's go back to the case of one element. So you have an integer and you want to ask which are the possible values for the index of A modulo P. So the index is a positive integer. You can ask, can we get all positive integers or not? And we already saw that in general, this index map is not surjective because we saw that if A is a square, the index can never be 1. But more something stronger than that, if A is a square, the index can never be odd. So let's see the image of the index map. So we make a decomposition for A. So namely, we try to write it as plus or minus a square, plus or minus a fourth power, and so on. So we try to write it as plus or minus a power with exponent, a power of 2, as large as possible. Okay, so once we do this, we have some epsilon, so the sign, which is plus minus 1, and we get a non-negative integer d. Then we look at this alpha. And this alpha, basically, we try to write it as a square. So square factors, we put them aside in some number, which we call b squared. Then maybe there is a factor 2 left, and we call it 2 to the delta, where delta can only be 0 or 1, because up to squares, there can be at most one factor 2 left. And then we could have odd factors left. So we could be left with an odd square-free integer, which we call t. But in fact, we also choose the sign such that t is congruent to 1 modulo 4. This is something a bit technical. But so in any case, you take your integer, you decompose it as I described, and you get parameters. So the parameters being, sorry, I have low battery. I have to plug it before something bad happens.
No problem. You can repair it.
Yeah, I saw low battery, and before the I said something bad happened. I have to So I just plugged in my computer the wrong cable, so I thought it was charging, but I was okay. In any case, sorry, I'm back. Okay, so you start with your integer, make the decomposition. And with the decomposition, you get parameters. So you get epsilon, which is plus minus 1. D is a non-negative integer. B is an integer. Delta is 0 or 1. And T is an odd square-free integer congruent to 1 modulo 4. And then the result on the image of the index map is that there are only few values of the index that you have to exclude. So namely, the philosophy is that the index map is surjective unless there are good reasons for it. So you take all values unless there are values which you have to exclude for good reasons. So what are the good reasons? Well, you exclude odd values for squares. This we already know. You exclude basically odd numbers times this t that you had above under some other conditions on the parameters. You exclude 2 times an odd number times this t that you had above. So here I put absolute value because the index consists of positive integers. But so in any case, the number that you exclude is the t above, making it positive, times here twice an odd number under other conditions on the parameter. And the last condition, which is the most complicated one, is that you exclude, so you exclude some other infinite set of values, but they are related still related to the number t that you had above. So if this t is divisible by 3, okay? So in fact, okay, I have it written here. So if A is a cube, is a perfect cube, and 3 divides t, you exclude some other values. So this list of cases is quite technical, but you can imagine that there are some conditions on the index. Sometimes the 2 must divide the index, and sometimes there are some small things that happen. But in general, this index maps tends to be surjective. And for example, if you take the index map for the integer 2, it's surjective. So all positive integers are the index of 2 modulo p for some p. And however, if you start taking more than one integer, for simplicity, just 2 integers a and b, the index map is never surjective. So this is a different phenomenon. And the reason of non-surjectivity, which is described in the paper, is quite easy. So you can see it as an exercise. You have your integers a and b and reduce them modulo p and look at the indices. If 4b divides the index of the first integer, then the index of the other integers cannot be odd. And this implication excludes you values of the index. So excludes you the tuples where the first number is divisible by 4b and the second number is odd. So this is reason enough to say that your index map cannot be surjective for any integers a and b. And clearly, as an extreme case, well, if you take a is equal to b, then you only get the constant tuples. So it's clearly not surjective, the map. But even if you take a and b multiplicatively independent, well, you still won't have surjectivity. So as I said, I just presented you the problems we worked on for Q. We did it more generally for number fields. And instead of integers a1 to an, we work with groups of finally generated groups of algebraic numbers, say in the full generality. So the fact that I like about my first paper with Ollie is that really we just attack this problem in the full generality. And still there are many, many things that we can say. Part of the results are under a condition that is the correct generalization of the elements being multiplicatively independent. So I think I can stop here and have some more time for questions, if any.
Okay, thank you very much, Professor Antonella Perucca. On behalf of the organizing committee, we want to express our gratitude for accepting to be plenary speakers at our conference. It's a huge honor for us. And thank you for respecting the time. So if there is some questions, then you are welcome. You can write it in the discussions, or you can see it directly to Professor, and she will give answers. Oui, Mr. Muhammad.
Thank you very much. Yeah.
Okay, Yeah, so
do you have
maybe
any information?
Okay, so maybe let me
this?
start by making the link between Kummer theory and Artin's conjecture. So the Artin's conjecture is a problem about reductions. So if you take number fields, it's a problem about reductions of number fields, and it mostly uses tools of analytic number theory because it's a problem about the density of primes. So that's analytic number theory. But as I try to explain you, naturally coming into the problems are cyclotomic Kummer extensions of your field. And what is important about them is namely only the degree. So you have to understand, so if you want to write down the density, you should understand the degrees of these extensions. And in particular, to study the degrees of this extension, you have to study the failure of maximality for the degree, because you expect, okay, maybe I just go back to the theorem. So if you have the cyclotomic extension, okay, it's here. So if you have the cyclotomic extension, Kummer extension, the degree is maximal if you have degree phi of n, Euler-Toten function. So here, okay, in this case, it's over Q, so it's surely maximal, but it could be not maximal over number fields. And then you have to basically tell the degree of the Kummer extension over the cyclotomic extension. And this Kummer extension, if maximal, it would have degree precisely n, but that may not be the case. So what I did independently of Artin's conjecture in the last years, I studied the failure of maximality for these degrees. And then, so this put me in a very good condition, because this is precisely tools which are needed for Artin's conjecture. So depending on what you like most, Kummer theory or Artin's conjecture, well, you can see one of them. You can say, okay, Artin's conjecture is an application of Kummer theory if you like more Kummer theory, or you can say, oh, I like Artin's conjecture, so I just do Kummer theory as a tool to study it. Okay, but what I was saying is that here it's only the degrees, so I am sure that there are plenty of open questions for these fields, like the one you mentioned, and I would be happy to discuss this more detail with you in the future, but I don't think that what you mentioned will be very relevant for this problem. And I would say luckily, because this keeps things simple. I mean, of course, if you have a number field and the only thing that you need to know is the degree, well, that's quite a good news.
Thank you very much.
Thank you very much. And we're just waiting if others have questions. Mr. Lakhmisi in the Radij, he just thank you for the excellent presentation.
Okay, so then I can just conclude by saying that Artin's conjecture will celebrate soon its 100th birthday. And in fact, now that I'm doing research on the subject, so I have various open problems with various kind of people on Artin's conjecture. So I entered the Artin's conjecture friends. So we are planning many things for the 100th birthday. So we are planning a book with a survey on Artin's conjecture. So the book is not ready, but it will be ready for 2027. And also some birthday conference of the conjecture. So just stay tuned. I will post on my website updates on this. So far we still have 4 years time, so we are not such in a rush. But yeah, I think in 1 or 2 years you can already maybe get some news about 2027.
Okay, thank you, Professor. We're just waiting for your book. You say 2027 in 4 years. Okay.
Yeah, luckily it's not only me writing the book. I'm the editor, so I will just write 1 or 2 chapters. Peter Mori is the other editor. He's also a super fan of Artin's conjecture. He wrote a very beautiful survey, and the idea I had was okay, this survey is totally nice and it deserves to be expanded and now extended with the recent progress. So we came to this idea of making this book, which looks like an adventure, but okay, we can do it. So stay tuned.
Okay, thank you. Good adventure in any way. Books are good adventures in any way. So I think we don't have more questions. So Professor Muhammad, if there is no question, we're just gonna thank Professor Antonella Perucca for her presence with us today and for accepting to be a plenary speaker, which honors us a lot. And thank you. Simply thank you very, very much.
Okay, yeah, well, thanks to you. It has been my pleasure. Bye.
Thank you very much.
So, have a break?
Yes. I think,
So,
Mr. Muhammad, we have a break until 12 o'clock.
Yes.
With Jaitra Chattopadhyay, Professor Jaitra Chattopadhyay.
Yes.
And 12 o'clock.
Okay.
So thank you. Thank for all the participants. So see you in almost 45 minutes or 48 minutes with the other talk. This session will be moderated by Professor Hanan Shuli. And for me, I just wanted to thank everybody for his presence here, which honors us. And thank you, Mr. Muhammad Shamsuddin, for the opening, and Mr. the Vice Dean of the Faculty of Sciences. Thank you, and see you in 45 minutes.
Thank you very much. See you.